Hello, my name is Peter Jang, and this video is to demonstrate the work that I've done in the project portion of my directed study under Professor Thomas Little in the ECE department and Professor Jonathan Rosen from the BME department. What you see here is a pretty basic web application. It was built with the Ruby on Rails framework, and it is currently backed by a SQLite database. Its main functionality is to take in user input, which will correspond to a patient's information, such as their age, their gender, the height of sternum relative to the table when they're laying down, and also their depth, which is relative to where the device is positioned. If we look into records, we'll find that all of the data entries of previous patients, and if we want to add a new calibration, we can go into the setup page and say we want to add a 25-year-old male whose height of sternum relative to the table is 15 inches and whose depth relative to the device is 17 inches. If we save that calibration, that all looks good, and we go back into records, and we'll find that we have our data in the current database, and if there's a duplicate, say a mistake, you can always delete one entry and you'll have one left. So when you're ready, you can click upload and it'll say device has been calibrated. That just means that the device that you've inputted is now being sent to the microcontroller, where it will be processed and where the microcontroller will then control the actual device. So if you can take a look at my computer screen over there, I know it's pretty small and faint. You'll see that I had just clicked upload, and so the device has calculated that this person that I have just inputted is actually under person B, which I'll explain later. And you'll see that the device is moving accordingly. The X is a fixed lateral motion, and the Y will be incremented according to the analysis. This is the analysis done by the BB2 team to calculate 3 different paths that the device can take for 3 different patients. If you imagine that y-axis to be height and the x-axis to be time in seconds, you'll see that the device's height changes exponentially over time. For testing purposes, the x motions were kept constant, incrementing 0.5 inches per measurement. So over 9 seconds, the device should have moved in the lateral motion 4.5 inches, and in height it will vary depending on which person the device is calibrated to. So to put this into practice, I've implemented some C code in the Arduino IDE. Just to explain what's going on here for a little bit, if it is person A that the preset calibration is set to, it'll enter this code block. If it is person B, it'll enter here. Person C, it'll enter here. Looking specifically at person B, since that is the last example that we've worked with, you'll notice that there's a for loop going from 0 to 9, and in each iteration there is a delay of 2,888 milliseconds. That just means that everything in this iteration will go on for 2,888 milliseconds. Now, the importance of this figure is that this is how long it takes for the device to reach 4.5 inches. I'm sorry, this is the time it takes to reach half an inch in either direction. So if the x direction, which is never changing and it will set to constant as I've mentioned before, if it runs for 2,888 milliseconds 9 times, then we know that it will reach the desired 4.5 inches by the end of the cycle. Now, the y direction, or the height variance, will change depending on a function listed here, which is the same one that we've seen before, the exponential function, except now it is scaled by milliseconds to stay compliant with the design. So the x direction, so the lateral direction, it'll constantly be changing 0.5 inches per iteration, but the y direction will be changing as a function of time, which is represented by I, which I know isn't really time, but it is our constructed version of time since it is scaled by 2,888 milliseconds. In this iteration, I've added a force resistive sensor to the claw of the device. Now the user will be able to view how many newtons of force are being applied to the sternum by the device through a serial monitor. For testing purposes, I've attached a piece of yarn to the back of the device and also to the claw of the device. I know that this is less than ideal, but hopefully this can serve as a proof of concept that force can actually be read. Excuse the text being cut off there, it actually reads force in newtons. Soon you'll see that as their tension increases in the string, so the force in newtons also increases. Thank you, Professor Rosen. It's been an honor to work for you and learn from you and also work alongside the BB2 team. I've learned a lot through this project and also through the cybersecurity research paper. Please know that I'm more than happy to post any code to a remote repository, whether it be GitHub, Bitbucket, or a Google Drive. And I can love to do whatever it takes to make the transition easier for the next team or the next person, whether it be me or someone else, to come in and continue this project. Thank you again for this opportunity.